This is Digital's VAXstation 3520-3540 workstation. The VAXstation 3520 uses 2 CPUs, and the VAXstation 3540 uses 4 CPUs in a multiprocessing workstation environment. The VAXstation 3520-3540 is a color 3D graphic workstation that incorporates symmetrical multiprocessing architecture in a VMS environment and asymmetrical multiprocessing in an Ultrix environment. It is a mid-range work system that provides better performance and more functionality than other microsystem-based workstations. This course provides you with the skills that you need to install, diagnose, and repair the VAXstation 3520-3540 workstation. In this lesson, we will discuss the importance and structure of symmetrical multiprocessing. The VAXstation 3520-3540 workstation implements symmetrical multiprocessing, or SMP architecture. SMP architecture is extremely important in a workstation because it supports compute-intensive applications such as graphics software more efficiently than other architectures. The SMP architecture provides the VAXstation 3520-3540 with CPU performance that is 5 to 10 times faster than the VAX 11780 system. In SMP, there are 2 or more CPUs in the system to share the workload. This differs from a system cluster because it is a fully symmetric design. In a system cluster, each CPU has its own memory and may have some mass storage devices that are not accessible to the other systems in the cluster. In an SMP environment, the processors share all memory and I/O devices. All CPUs execute operating system code from a single global memory. They are all able to execute in kernel mode. All CPUs in an SMP environment are equal. No one processor controls or assigns tasks to the other processors in the system. To understand how SMP works, it is important to understand the operation of cache memory. In this lesson, we will present a generic overview of cache memory and its operation. Cache memory is a small, very fast storage unit that is actually a part of the central processor. Cache memory is placed between main memory and the rest of the central processor. Cache memory holds a copy of information most recently accessed in main memory. When the processor needs information, for example, data 1, it first looks in its cache memory. If the information resides in cache memory, it is accessed directly, thus saving time by avoiding access to the relatively slower main memory. This is referred to as a cache hit. If the requested information is not in cache memory, for example, data 3, it is called a cache miss. When a cache miss occurs, the processor must access main memory to retrieve the requested information. In addition to retrieving the information that was specifically requested, cache memory also retrieves and stores additional information from main memory. Cache memory works because it can successfully predict which information a program is likely to require next. Programs have a tendency to make most memory accesses in the vicinity that was just accessed. Because cache memory automatically retrieves additional words each time it accesses main memory, the chances are good that the next request for information will result in a cache hit. When all locations in cache memory contain information and a new request for information results in a cache miss, the information that is retrieved from main memory will be written over the least recently used information in cache memory. The information that is involved in a cache transaction is referred to as a cache line or a cache entry. A cache entry consists of a data field and a tag field. The tag field holds information about the corresponding data. This information includes the main memory address, a valid bit, and a dirty bit. The dirty bit, when set, indicates that the data has been modified while in cache. There are 2 types of cache memory: write-through cache and write-back cache. Each handles data that is modified while in cache differently. In a write-through cache, when the data resident in a cache entry is modified, for example during an increment operation, the updated data is always passed through cache memory and written into the corresponding location in main memory. Thus, main memory is always up to date. In a write-back cache, when a cache entry is modified, for example during an increment operation, the dirty bit is set in the cache tag field, indicating so, and the corresponding location in main memory is left unchanged. Thus, the cache memory is updated and the main memory is invalid. When the write-back cache is full and a cache location is needed, the CPU checks the tag field of the line that will be written over by new information. If the dirty bit is set, the updated information is written back to main memory before the location is written over. The VAXstation 3520-3540 workstation uses both write-through and write-back caches. We will discuss the uses for each type of cache memory later in the course. For SMP to work effectively, certain hardware requirements have to be implemented by the system. In this lesson, we will discuss these requirements. SMP architecture requires one primary and one or more secondary processors. The primary processor is the only processor that is allowed to access the console terminal directly. Secondary processors communicate with the console terminal by using the primary processor as an intermediary. The primary processor is selected when the system is initialized at power-up. Typically, the primary processor is the processor with the lowest CPU identifier. In the case of two processors, for example, one with a CPU ID of 0 and the other with a CPU ID of 1, the processor with a CPU ID of 0 is usually selected as the primary processor. In the VAXstation 3520-3540, CPU ID is determined by the backplane slot. Note that all processors have the ability to be the primary processor, and therefore have the ability to access the console terminal. However, once a processor is established as the primary processor, it is the only one that is allowed to access the console terminal directly. The console system uses only one console terminal for all processors. All console output messages from all processes are displayed on the same console terminal. Console input can be directed to any halted processor. Each CPU has several specific privileged registers. Among other things, these registers enable the CPUs in the VAXstation 3520-3540 system to determine the number of processors in the system and their status. All CPUs in an SMP environment must be at the same hardware and firmware revision level. The next SMP requirement that we will discuss is cache coherence transparent to the software. Cache coherency ensures that the information used by any CPU in the system is always valid. The most up-to-date information may not be resident in main memory, but may instead be located in another CPU's cache. Let's look at how this feature works. Since cache memory is a part of the CPU, in a multiprocessing system such as the VAXstation 3520-3540, there are multiple cache memories. Suppose that CPU A in a multiprocessing system decodes the instruction increment long word R2. Register 2 contains the memory address 1200, which contains the data 5. The CPU first looks in its cache for an address match, which in this case results in a cache miss. It then retrieves the data from main memory and puts the information into its cache. Next, it performs the increment operation. Since the data has been modified, it tags the location in cache as dirty. At this point, the main memory has not been updated. Now suppose that CPU B decodes an instruction involving the same memory location. If it retrieves the data from main memory, it will be using invalid data. To prevent this problem from occurring, the VAXstation 3520-3540 uses a hardware Snoopy cache to ensure cache coherence. A Snoopy cache determines where the most up-to-date information resides and ensures that the current information is used. The Snoopy cache and cache operations specific to the VAXstation 3520-3540 will be discussed in more detail later in this course. Just as the standard VAX hardware needs to be updated to support SMP, so does the software. In this lesson, we'll discuss the changes in the VMS operating system that make support of SMP possible. VMS version 5.0 is the first version of digital operating system software to support symmetrical multiprocessing. Let's look at some examples of problems that can arise if two or more processors try to access the same resource simultaneously. Then we will discuss how VMS avoids these problems. Suppose a man goes into a bank and deposits a $300 check in his account, which has an existing balance of $50. Then he withdraws $200 in cash. The outcome of this transaction is the same as depositing $100, but it is done in two steps, a deposit and a withdrawal. Suppose the man's wife is at another branch of the bank and, hypothetically, she checks the account balance at a moment in between his two transactions. She sees a balance of $350 and decides to withdraw $200. If both parties actually withdrew $200, it would overdraw the account by $50, but no one would notice the error until later. These types of problems are prevented under VMS because each major resource is protected by an associated spin lock. Basically, a spin lock is a data interlock imposed by the software. This means that only one processor can access a resource at a time. All other processors are locked out until the spin lock is released by the first processor. The processor releases the spin lock after it has completed its operation. Another way to look at this is to say that the spin lock is like a key to a room that is always kept locked. Anyone that wants to access the room must first get the key. If someone else wants to use the room at the same time, the key will not be available, and they will have to wait for the first person to return it. If spin locks had been used in our earlier example about the bank, the wife would not have been able to access the account and retrieve the balance until her husband finished his transaction. This wait is usually transparent to the user. Let's look at an example using spin locks. Two processors, A and B, each need to access two resources, X and Y. They begin at just about the same time. Processor A manages to gain control of resource X first and locks out processor B. Processor B can't use the resource X until the lock is lifted, so it goes to the next step, which is to gain control of resource Y. This locks out processor A from resource Y. Now, neither processor can complete its task. They are both spinning their wheels, waiting for the opposite processor to release the other spin lock that they need. This situation is called deadlock. To prevent a deadlock situation in VMS, spin locks must be acquired in a predefined order. Each spin lock has a rank associated with it and must be acquired in order of increasing rank. In our example, we can see that resource X has the higher rank of the two. Remember that processor A acquired resource X first. Processor B has not only been locked out of resource X, it can't acquire resource Y either, because it must acquire resources in order of rank. Therefore, it needs to acquire resource X before it can acquire resource Y. Thus, with this ranking system, deadlock is prevented. The features that we have discussed enable VMS to overcome typical SMP environment problems. This concludes the introduction to the SMP module. The VAXstation 3520-3540 is a CVAX-based symmetric multiprocessing workstation designed for compute-intensive and 3D graphics applications. The VAXstation 3520-3540 is designed for 4 market applications: 3D mechanical CAD/CAM, 2D CAE, scientific research, and imaging. The VAXstation 3520-3540 is supported by 2 operating systems, VMS and Ultrix. The minimum version of VMS that is supported is version 5.1-1. The minimum version of Ultrix workstation software that is supported is version 2.0a. The VAXstation 3520-3540 uses the VR295 monitor with a standard LK201 keyboard. The corporate mouse is used and a graphics tablet is optional. Let's take a closer look at the system. The VAXstation 3520-3540 uses the standard BA213 system box. The system box uses the same outer plastics as other systems with which you may be familiar. It also uses the same card cage, the same modular power supplies, and 4 cavities for mass storage devices. However, the VAXstation 3520-3540 uses a unique 12-slot backplane. The slots are numbered 1 through 12 from right to left. The VAXstation 3520-3540 is not a Q-bus system. The first 9 slots of the backplane have Comet connectors and hold L-series modules. Here is an L-series module with Comet connectors. Note the spacing and the number of pins as compared with a Q-bus module. The last 3 backplane slots are available for QBus peripherals in an optional configuration. The basic system configuration consists of 1 dual CVAX processor module, 1 memory module, 1 I/O module, and 2 modules that make up the graphics subsystem. Optional devices include a second dual CVAX processor module, a QBus adapter module, up to 3 additional memory modules, a 16-plane graphics expansion module, up to 4 RZ55 disk units, 1 RRD40 CD-ROM disk drive, and a TK70 cartridge tape unit. If a cartridge tape unit is installed, physical limitations of the BA213 box restrict it to the first or rightmost I/O cavity in the system box. The operator panel is mounted in front of the second I/O cavity. It allows the user to perform a limited set of functions on the system, such as halt and restart. It also contains LEDs that indicate system power and run status. This concludes the video portion of the physical description unit. In this lesson, we'll discuss the system as a whole. It will help you to understand how the major subassemblies work together. This is a block diagram of the VAXstation 3520-3540 workstation. This diagram shows all available options. In reality, all of these options could never be installed in the same system box due to the physical restrictions of the backplane. The CPUs, memory, graphics base module, I/O, and QBus adapter communicate through the M-bus. The M-bus is a synchronous memory interconnect between the VAXstation modules. The M-bus supports a maximum of 7 modules that arbitrate for the M-bus using a least recently used priority distributed resolution scheme. In other words, each M-bus device has an interval timer that is reset when it becomes busmaster. When 2 or more devices request the bus simultaneously, control will go to the device that has the longest amount of time in its timer. A list of M-bus signal names and pin assignments are located in the appendix section of the VAXstation 3520-3540 maintenance guide. More specific information on M-bus signals and transactions can be found in the VAXstation 3520-3540 system specification. Each module that interfaces with the M-bus does so through the Functional Bus Interface Chip, or FIBIC. The FIBIC is a 3-port multi-purpose bus interface and cache controller. The 8-plane graphics module and the optional 16-plane graphics expansion module signals are connected to the graphics base module through the High Density Interconnect, or HDI. This is also known as the graphics front plane because it connects the handle side or front of the modules. These same 3 modules also communicate through the backplane through the Video Interconnect, or VI bus. Mass storage devices are connected to the system through the Small Computer System Interconnect, or SCSI bus. This is sometimes referred to as the SCSI bus. The QBus is available to connect additional options. In order to utilize the QBus, however, the QBus adapter module must be installed. In this lesson, we'll discuss the unique VAXstation 3520-3540 backplane. This is a diagram of the VAXstation 3520-3540 backplane. As you can see, the backplane contains 3 separate buses. The first 3 slots are dedicated to the graphics subsystem. The 3 graphics modules are connected by the buffered VI bus on the backplane side. The M-bus runs along the bottom half of slots 3 through 9. The QBus runs along the top half of slots 9 through 12 and then down to the bottom half of the backplane and back across slots 12 through 10. If the QBus adapter module is installed, a limited set of QBus modules may be installed in slots 10 through 12. The QBus adapter module, if installed, must be placed in slot 9 because it communicates with both the M-bus and the QBus. The graphics base module must always be installed in slot 3 because it communicates with both the M-bus and the VI bus. Other M-bus modules can be installed anywhere along the M-bus, including slot 9, if the optional QBus adapter module is absent. Considering the M-bus arbitration scheme, there is no advantage or reason to place modules in a certain order. However, the I/O board is usually installed in slot 4. The CPU and memory modules in a base system are usually installed in slots 7 and 8 respectively. This provides a load for the second or left power supply. When adding options to an existing system, always try to balance the load between the two power supplies. There are no grant continuity cards required on the M-Bus, even if a slot is skipped. As in other Q-Bus backplanes, if the modules are installed in order, there is no need for grant continuity cards. However, if a slot is skipped, a grant card must be inserted into the skipped slot to provide bus continuity. Refer to the VAXstation 3520-3540 Maintenance Guide for the list of supported Q-Bus modules. At least one KA60 module is required in all VAXstation 3520-3540 configurations. The VAXstation 3520-3540 KA60 dual processor module consists of two functionally independent CPUs that share a single set of bus transceivers, clocks, and test mode connections. A second dual processor module may be installed, which provides 4 CVAX processors. The maximum number of processors supported by the VAXstation 3520-3540 workstation is 4. Because of the symmetry of the KA60, the functionality of processor A is the same as that of processor B. We will discuss one processor in this lesson, but the information is applicable to either processor. The KA60 CPU module uses the same CVAX CPU chip that is currently used in Microvax 3500-3600 series systems. The CVAX chip incorporates all standard VAX features. To accelerate floating point operations, each CVAX has a companion floating point accelerator, or FPA. The FPA supports VAX floating point instructions and operates on F floating, D floating, and G floating data types. It also accelerates execution of certain integer instructions. The diagnostic boot ROM provides a total of 128 kilobytes of system boot information, as well as self-test diagnostic firmware for each CPU. The M-Bus interface consists of one FIBIC per processor. The FIBIC provides the hardware necessary to determine the number and status of all CPUs present in an SMP configuration. It also serves as the M-Bus interface and cache controller. Each processor implements a red quad LED to report processor status. A single green LED indicates the module OK signal. The VAXstation 3520-3540 uses 2 levels of cache memory, sort of a cache within a cache. In this lesson, we will discuss the operation and interaction of the 2 levels of cache. The VAXstation 3520-3540 Level 1 cache is internal to the CVAX processor. It stores both instruction and data stream references and is maintained as a subset of the external Level 2 cache. Each entry consists of 8 data bytes with byte parity, a 20-bit tag with a parity bit, and a valid bit. Internal CVAX error checking verifies data and signals parity errors on the Level 1 cache. The Level 2 cache is the external Snoopy cache. Each VAXstation 3520-3540 Snoopy cache services its attached CVAX processor and monitors the system M-Bus to provide other caches with the contents of memory locations it has cached. Because all Level 2 caches monitor memory space bus transactions, they can continually determine whether cache entries are exclusively in their cache or are shared by 2 or more caches. The Snoopy cache can also determine whether an entry has been modified. The Snoopy cache uses this status information to maintain system-wide cache consistency and to minimize the M-Bus bandwidth. The Snoopy caches use a write-back function for unshared entries and a write-through function for shared entries. Each entry in the Level 2 cache consists of an octaword data store and a tag store. The tag store contains the main memory address with bit parity, a valid bit, and 2 state variables that represent the 2 independent properties of each entry. These properties are shared and dirty. The shared property indicates whether the entry is present exclusively in this cache or is resident in 2 or more system caches. If a cache entry is shared, writes to this location initiate an M-Bus write-through transaction to invalidate the shared entries in other caches. If a cache entry is not shared, writes to this location do not generate bus traffic. The dirty property indicates that the entry has been modified in the Level 2 cache but has not been updated in memory. Dirty entries must be written back to main memory if a miss requires use of the dirty entry's location in the cache. This write-back operation is called a victim write. The combination of shared and dirty properties results in 4 possible states for each cache entry. They are not dirty, not shared, dirty, not shared, not dirty, shared, and dirty, shared. The state of the Level 2 cache entry determines the manner in which the data cycle is accomplished. Let's look at a read and write cache cycle. First, we will discuss an example of a cache read. The cycle begins when CPU-A issues a memory space read. First, it looks to the Level 1 cache to see if the data resides there. If it does, the CPU uses this data and continues with its operation. If a Level 1 cache miss occurs, the Level 2 cache probes its tag store to determine if the requested location is present in its cache. If the tag probe results in a hit, the Level 2 cache presents the data from the Level 2 data store to the CPU, which stores a copy in the Level 1 cache. In the event of a tag probe miss, the Level 2 cache begins a memory read cycle to retrieve the data from main memory. During the memory read cycle, all other Level 2 caches probe their tag stores to see if the requested location is present in their cache. If a hit results, the cache controller sets its shared bit and asserts the mShared signal. This informs the processor that issued the memory read to also mark the cache line shared. If the tag hit references a dirty line, the cache controller arbitrates to provide its data to the MBus master. CPU-A aborts the memory read cycle and copies the data from CPU-B's cache into its own Level 2 cache. This ensures that modified data resident in cache is used in place of invalid memory data. If the shared entries are clean, the CPU continues to retrieve the data from main memory, because it is faster to continue than to abort the cycle and get the data from another cache. In any case, the Level 2 cache retrieves the information it needs and stores it. The CPU then retries the read cycle and this time gets a Level 2 cache hit. Next, we will discuss a cache write cycle. When the CVAX issues a memory space write, the Level 2 cache probes its tag store to determine whether the requested location is present in the cache. If the tag probe results in a hit, the Level 2 data store is updated by the CVAX and the dirty bit is set for the cache line. The corresponding Level 1 cache entry is invalidated if it's there. If the tag field has the shared bit asserted, indicating that the data is present in one or more other caches, the CVAX will generate a write-through cache transaction to the MBus. Any other Level 2 cache that shares the location will invalidate its entry. Whenever a Level 2 cache entry is removed or modified, the cache controller invalidates the corresponding entry in Level 1 cache if it's there. If, when the CVAX issues a memory space write, the Level 2 cache tag probe results in a miss, the Level 2 cache retrieves the requested information from main memory and fills the data store with the requested line. The CVAX hardware retries the write cycle, which now results in a Level 2 hit. You may have noticed that during a cache memory write cycle, the CVAX did not probe the Level 1 cache first. This is because the Level 2 cache needs to be updated to ensure cache coherency. Whenever the Level 2 cache is written to, the corresponding entry in the Level 1 cache is invalidated. To update the Level 1 cache first would be a waste of time. In an earlier lesson, we learned that if a read or write miss occurs when cache memory is full, the information retrieved from main memory is written over the least recently used information in cache memory. The line that is written over is called a victim line, and the operation is called victim processing. Whenever a read or write miss occurs, victim processing is initiated before the data store is filled with a requested line. If the victim line is dirty, the Level 2 cache controller issues an MBus memory victim write. This flushes the dirty line back to memory. After victim processing is complete, the cache controller issues an MBus memory read to obtain the requested line. While reading the data from memory, the cache controller performs a CVAX cache invalidate cycle to remove the victim line from the level 1 cache if it's there. When the M-bus read is complete, the data store is updated with the requested line, the tag store is updated with a new address, the shared bit is set to the correct value, and the dirty bit is cleared. If the victim line is clean, the level 2 cache performs the same operations except that it skips the M-bus memory victim write. In this lesson, we'll discuss the VAXstation 3520-3540 memory. The two supported memory options for the VAXstation 3520-3540 are the MS60AA and the MS60BA memory modules. They both contain ECC-protected dynamic random access memories, or DRAMs. Their functions are to respond to the M-bus protocol and to retain and retrieve data used by the VAXstation 3520-3540 processors and I/O subsystem. The memory modules do not have battery backup capability. All data will be lost in the event of a power failure. The MS60AA storage capacity is 8 megabytes, while the MS60BA storage capacity is 16 megabytes. In addition, they both have the ability to perform self-test and initialization of their DRAM array on command from a processor. The 8 megabyte and 16 megabyte memory boards may be combined in the same backplane. In this case, the 16 megabyte board or boards are typically installed on the bus ahead of the 8 megabyte boards. In this lesson, we'll discuss the VAXstation 3520-3540 graphics subsystem. The graphics subsystem is a high-performance video subsystem capable of executing both 2D and 3D display lists. It generates high-quality video images. In addition to general-purpose graphics output, the video subsystem provides the primary console port for the VAXstation 3520-3540 workstation. The module set consists of the graphics base module, the graphics output module, and optionally the graphics expansion module. The graphics subsystem supports configurations of 8 or 24 video planes. An 8-plane subsystem can be upgraded to 24 planes with the addition of the graphics expansion module. Both configurations support the VR295 color monitor and use the HDI front plane for over-the-top connections. This is a block diagram of the graphics subsystem. It consists of a CVAX CPU CFPA, YTEC 3D transformation engine, a FIBIC, a 1 megabyte DRAM, a 128 kilobyte diagnostic ROM, VI bus transceivers, a low-end graphics subsystem or LEGS chipset, video random access memory, a video output chipset, and the VR295 color monitor with associated cables. The functional blocks are connected by the VI bus. The section of the VI bus that is internal to the base module is the same as the PIN bus with which you are probably familiar. The VI bus extends throughout the subsystem through the backplane and front plane. The section of the bus that is external to the base module is referred to as the buffered VI bus. The FIBIC performs all interface functions needed for the M-bus and VI bus to communicate synchronously. The CVAX CPU is the default VI bus master. It runs synchronously with the graphics subsystem. The YTEC 3D transformation engine is a high-speed processing unit designed to transform 3D graphics display lists into 2D input commands for the LEGS chipset. All support for graphics rendering is provided by the LEGS chipset. The address chip or A chip is the controller for both the VI bus and graphics operations. All clock signals required for synchronous operation are generated here. The data chips process pixel data during hardware-assisted operations and provide the data path between the buffered VI bus and 4 planes of display memory. The graphics subsystem architecture supports up to 7 data chips for a maximum of 28 planes. But the VAXstation 3520-3540 uses a maximum of 6 data chips or 24 planes. 8 video planes reside on the output module as shown here in the standard configuration. Support for 16 additional planes is available with the optional graphics expansion module. We will take a closer look at the expansion module in a minute. The timing chip controls the loading and output of display memory data, the loading of data for the video output chips, and the generation of monitor timing signals. The graphics subsystem supports 1 megabyte of local DRAM. The DRAM controller is implemented by the A chip. All memory control signal and address lines are connected directly to the A chip, and data lines are connected to the VI bus. The 128 kilobyte onboard diagnostic boot ROM contains LEGS module ID information, self-test diagnostics, CVAX boot code, and microcode that is necessary to run the VAXstation 3520-3540 console. Diagnostic LEDs are present to externally monitor the state of the module set. The HDI front plane has 4 red LEDs that indicate diagnostic status. There is a green LED on the graphics base module that indicates the status of the self-test diagnostics. The graphics expansion module consists of 4 data chips and 16 planes of video memory. It enables the VR295 monitor to display 24-bit planes of true color graphics. Let's take a closer look at the data flow. During normal operation, graphics packets are assembled in system memory by the host CPU. They are then transferred under control of the CVAX from system memory to local DRAM. Once in local DRAM, the graphics packets are parsed and executed by software running on the CVAX and the YTech 3D transformation engine. In general, the CVAX is responsible for handling 2D packets and all register loading for the LEGS chips. The YTech 3D transformation engine is responsible for transforming 3D packets into 2D packets that are returned to DRAM. The CVAX then loads the 2D packets into the LEGS chips. The CVAX writes video output chip commands through the D chips to a reserved section of VRAM. From there, the video output chips are loaded during vertical blank time. Consequently, the host and CVAX are relieved of having to synchronize the video output chip register loads with the monitor timing. Finally, the data is passed onto the monitor and the graphic image is painted on the screen. In this lesson, we'll discuss the Workstation I/O subsystem, which consists of the Workstation I/O module and the I/O cover assembly. Most computer systems have a disk controller, a tape controller, an interface for communication devices, and a network interface module as peripheral option controllers. In the VAXstation 3520-3540, all these devices are included on the Workstation I/O module. In addition to the I/O device controllers, this module has a system support chip that includes a time-of-year clock, interval clocks, and a battery backup RAM that stores workstation configuration parameters. There is a PHYBIC that serves as an M-bus interface, and a workstation ROM that contains self-test diagnostics for the I/O logic and devices. The network interface supports either standard or thin-wire Ethernet. It has a network data buffer because of latency constraints. This is a DZ-compatible serial interface. There are 4 asynchronous lines available for use by a keyboard, mouse or tablet, modem, and a printer or auxiliary console. The disk and tape interface is the controller for the SCSI bus and associated mass storage devices. Currently, the RZ55 and RRD40 CD-ROM disks are supported. The maximum configuration for SCSI devices is 4 RZ series disk drives and 1 CD-ROM disk. The I/O signals are made available externally by a 50-pin ribbon cable that connects to the I/O cover assembly. The cover assembly contains a 15-pin connector for the keyboard and mouse or tablet serial lines. This connector supplies plus 5 volt, plus 12 volt, and minus 10 volt DC power, as well as data and control lines for the keyboard and mouse or tablet. A printer or console serial line on a 6-pin connector. The cover module uses a single hexadecimal digit display with a decimal point for the status output display. Refer to the VAXstation 3520-3540 maintenance guide for the status code definitions. A 25-pin connector for a modem serial line. A standard Ethernet transceiver line on a 15-pin connector. A thin-wire Ethernet tap. This switch selects standard or thin-wire Ethernet output. Both are supported, but not at the same time. The reverse side of the cover assembly contains a logic module that acts as an interface between the I/O cover cable and the I/O connectors. It contains the thin wire transceiver logic and the drivers and receivers for the serial lines. This battery is used by the workstation I/O module during power failures to maintain the time of year clock and battery backup RAM. If the I/O cover cable is disconnected, the battery is also disconnected, and the information in the toy clock and the BBU RAM will be lost. To access the Q-bus section of the backplane, a Q-bus adapter module must be present in the system. In this lesson, we'll discuss this module. The Q-bus adapter module very simply acts as a translator between the M-bus and the Q-bus. The Q-bus adapter module contains an M-bus interface or FIBIC, a Q-bus interface, a diagnostic boot ROM, and status indicators. It uses a common bus internal to the module. During a data write, data passes through the FIBIC, where it is translated to common bus data. Then it is passed over the common bus to the Q-bus interface, where it is translated into Q-bus data for use by the appropriate Q-bus device. During a data read, this process is reversed. In this lesson, we'll discuss the VAXstation 3520-3540's power supplies. The VAXstation 3520-3540 system box supports two H7868 power supplies that are plugged directly into the backplane. The H7868 provides a plus 5-volt output to the logic and a plus 12-volt output to the communications options and RZ series disk drive motors. The right power supply is the primary power supply. It provides power to the right half of the box, slots 1 through 6, and to the two rightmost mass storage cavities. The left power supply provides power to the left half of the box, slots numbered 7 through 12, and to the two leftmost mass storage cavities. Each power supply has a fan output that can drive two 4.5-inch DC brushless fans. In a BA213 system box, the right power supply drives both fans and the left power supply fan output is not connected. Each power supply has a resettable circuit breaker for overload protection. A recessed switch on the front of the power supply will allow a full power-down, power-up sequence of power OK and DC OK signals without removal of the input power. This in effect resets the VAXstation 3520-3540 workstation. Each power supply has a green LED that indicates power OK when illuminated. This is the operator panel. It allows the user to perform a limited set of functions on the system. In this lesson, we'll discuss these functions. Starting on the right side of the panel is a green power OK indicator. It is illuminated when the system is powered up and both power supplies produce the DC OK signal. Next to this indicator is the halt switch. It is a momentary switch that halts the system when pushed. It contains a red LED that is illuminated when the halt button is pushed in. The push button to the left of the halt switch is the restart run switch. It is a momentary switch that resets the system and initiates the system's self-test diagnostics when pushed. The restart run switch contains a green LED that indicates the system is in the run state when illuminated. If the system is in console mode and the halt switch is enabled, the restart run switch will blink to indicate that the system is in transitional mode. This concludes the functional description unit. In this lesson, we'll discuss the diagnostic strategy for the VAXstation 3520-3540 workstation. The strategy consists of 3 tiers of diagnostic testing that should enable you to isolate a problem to the failing FRU. The first testing tier is a power-up self-test, or PST. The PST is a fast, effective check for solid faults. Successful completion of the PST provides a high level of confidence that the system can boot. It tests all M-bus modules. In addition, the PST auto-configures any Q-bus options and SCSI devices that are present in the system. The PST runs automatically on system power-up. Alternately, selected portions can be activated from the system console program. The second testing tier is a system test that also tests all standard modules in the system. It differs from the PST because it tests modules concurrently rather than one by one. It is, therefore, a closer approximation of a real user environment. The system test is started from the system console. The third testing tier is for utilities such as disk formatting, NI loopback, and monitor test patterns. The PST can be activated in one of three ways: by powering up the system, by pushing the Restart Run push button on the operator panel, or by pushing the Power Reset button on one of the power supplies. While the tests are running, a countdown is displayed on the monitor and the LED display on the I/O cover. The test number that is presently being run is displayed. If an error is encountered, that particular test is aborted and the PST continues. Upon completion, a summary of all errors is output to the console. Remember that the PST only sees the M-Bus modules, so any devices that are not physically on the M-Bus are considered to be an extension of the module that connects them to the M-Bus. For example, the entire graphics subsystem is considered one device. The monitor also displays some information about each CPU. It lists the CPU number. It lists E1, which indicates that the CPU is enabled. If the CPU is disabled, E0 is displayed. And it lists P1, which indicates that the CPU self-test has passed. If the CPU self-test fails, P0 is displayed. The bottom line identifies the primary CPU. This is reiterated by the console prompt. The LED display on the I/O cover module displays .0 upon successful completion. If an error is encountered, the LED display indicates the physical slot number of the module or subsystem in error. If two or more errors occur, the display indicates the board with the highest slot number that had an error. The PST diagnostics report errors through LEDs on the modules and numeric error codes displayed on the console terminal. These error codes and their meanings are listed in the Testing and Troubleshooting section of the VAXstation 3520-3540 Maintenance Guide. Next, we will discuss how to run individual tests. Test 50 displays the system configuration and error status. To run it, type T for test, 50, and a carriage return. For each module on the M-Bus, the console terminal displays the module ID number, the contents of the module type register located on the FIBIC, the module part number, and the slot number where the module is installed, along with flags for any errors that were encountered. Soft errors are identified with one question mark, and fatal errors are identified with two question marks. The module ID or MID number is used by the diagnostics to reference the modules when it calls in tests from ROM and when it reports errors. The MID number is backplane slot dependent, not device dependent. For example, a dual CPU module that's installed in slot 7 in a system has a different MID number than if it were installed in slot 6. The MID number differs from the physical slot number, so make sure not to confuse the two. All VAXstation 3520-3540 diagnostics are ROM-based. As we discussed earlier, each M-Bus module contains a ROM on which diagnostics for that module reside. On other systems, when you want to test a specific device, you need to specify the device name or a diagnostic name to invoke the desired test. For the VAXstation 3520-3540, you must specify the MID number to invoke tests for a specific device. For example, the module configuration for the system shown lists the MID number for the L2003 I/O module as 5. One test that is useful to run on the I/O module is the device status test. To see the status of the devices on the I/O module, look at the configuration of the module itself. To do this, type T, space, 50, space, 5, carriage return. T for test, 50 for configuration, and 5, which is the MID number for the device that we want to test. This time, the console gives us the same information for the I/O module as the higher-level system configuration test, plus it states the revision of the diagnostic ROM and lists the individual devices being tested on that particular module. For example, Test 1 tests the system support chip and Test 2 tests the DZ interface. The output also shows status information about each individual test. You need only to be concerned about the last digit of this code. It provides you with error status information. A 1 in this position indicates successful completion. A 0 in this position indicates a warning, such as a missing loopback, and a 2 or a 4 in this position indicates a diagnostic failure on that device. Just as in the higher level display, subsystem errors are flagged by 1 or 2 question marks. Here, a warning is indicated for the NI subsystem because we ran the test without a loopback installed on the NI port. An individual test can be run by specifying the MID and test number. For example, to test the network interface for this system, type T for test, 5 for the I/O module MID number, 3 because the test number 3 is the NI test, and a carriage return. In this case, we have added a loopback, and now the test passes. The tests that are called up in this manner are the same tests that make up the PST diagnostic string. To loop on a test, one step is added to the last command. Type an R for repeat at the beginning of the command. The console will display an update to the status after every pass. To stop the loop, type Ctrl+C. The test will stop upon completion of the pass that is being run. When an individual PST test is run, the status is always reported to the console terminal. If you attempt to run a test that doesn't exist, such as test 500, the system will not report an error. However, we know the test was not run because there was no status information given. The EEPROM-based system test does a concurrent test of all the devices in the system. It has 2 modes of operation, customer mode and field service mode. There are different levels of test coverage and capabilities for both modes. While in field service mode, you have a choice of running a single pass or running continuous passes. To invoke the customer mode system tests, type T, 100, and a carriage return. Before you can invoke either single pass or continuous field service mode system test, you will need to do 2 things. First, install the field service mode turnaround on the modem port of the I/O cover module. This turnaround is shipped with a CD kit, along with other device turnarounds that are used for specific device tests. Once the special turnaround is installed, enter field service mode by running test 200 on the console. The command for the single-pass field service mode system test is T101. To invoke a continuous run of field service mode system test, the command is T102. To stop the continuous run, type Ctrl+C. To exit field service mode, first remove the field service mode turnaround, then run test 200 on the console. Failure to do these steps in this order could cause the system to remain in field service mode. This could result in someone inadvertently destroying customer data. If you try to run field service system mode test without first setting the system to field service mode, the test will abort with a test mode violation failure. Let's look at the console display of a system test. The top line of the error report is the header information, which includes the CPU board name, the system test version number, customer or field service run mode, and the runtime of the system test. The next section displays the device error and status report. As with the PST, the graphics subsystem and all QBus devices are each shown as one item. Each line of this report consists of a single or double question mark if there are errors, the MID number of the module being tested, the device mnemonics, a status and error field. Refer to the VAXstation 3520-3540 maintenance guide to decode these fields. The pass count. Runtime. There may be an S after the runtime in the device status line. This indicates that there is an extended screen containing additional information about the device. The extended screen may be viewed at the completion of the test. The last item shows the current location in the diagnostic code. When the system test encounters an error on any device, that device is dropped from the test and will not be tested on future passes. A single pass of the test will run through each device at least twice, then give you the option to view the individual summary displays. If you select No, the system will return to console mode. If you select Yes by hitting a carriage return, an extended information screen will be displayed for each device in the system, one at a time. You will have the option of exiting after any displayed screen. After all screens have been displayed, the system summary screen will again be displayed. You will still have the options to continue to view the extended screens or to exit. Here we choose to exit by typing an exclamation point. If you are running in continuous mode, the system test will continue until you abort it by typing Control-C, at which time you will be prompted for the option to display the extended summary screens. Another test that you may find useful is Test 201. Test 201 is an error analyzer. Each PHYBIC contains an error logging register. When an error occurs, pertinent information is written to the PHYBIC. The register is only big enough to hold one error, so only the information from the first error is saved. Test 201 displays the error logging information from the registers that reside in the PHYBICs. It calls out the dominant error with the MID number of the module or subsystem that is most likely causing the failure. This test is useful in finding software problems as well as software-detected hardware problems. A support engineer can help you analyze the error information. This concludes the video portion of the diagnostics unit. This section of the course describes the installation procedures for the VAXstation 3520-3540 workstation. Before installing the system, make sure that the site conforms to environmental and safety requirements described in the VAXstation 3520-3540 installation guide. Unpack the cartons and check the contents with the order sheet or packing list that is shipped with the system to make sure that nothing is missing. The VR295 is very heavy, and it requires 2 people to unpack and install it. De-skid the system unit by following the directions on the carton. Make sure that the on-off switch on the system box is set in the off or 0 position. Roll the cabinet to the selected location. Release the mass storage device shipping brackets by loosening the 4 retaining screws. Once the brackets have been released, tighten the screws again so they don't become bent or lost. Place the monitor on a flat workspace and make sure that the power switch is in the off position. Find the video cable and attach the signal cables to the matching connectors at the back of the monitor. Connect the keyboard cord to the connector block on the video cable assembly. Attach the pointing device to the connector block on the video cable assembly. At the system unit end, the video cable assembly splits into a keyboard pointing device cable and 3 signal cables. Slide the system unit end of the video cable assembly under the back of the system unit and pass it up through the opening between the metal chassis of the system unit and its plastic base. The signal cables attach to the matching connectors on the graphics cover. The keyboard pointing device cable connects to the I/O cover module. If there is an Ethernet cable, connect it to the I/O cover module and set the Ethernet switch to the correct position. Attach any peripheral options such as a CD-ROM disk, printer, or modem. Refer to the instructions that were shipped with the device for the specific installation procedures. Connect the power cords to the system box and the monitor and plug them into the wall outlet. Adjust the tilt on the monitor to a comfortable position. Power up the monitor, system unit, and any peripheral options that may be present. The system power switch should glow orange. The power OK indicator on the operator panel and the monitor power indicator should glow green. The system will now test itself. Possible system problems are indicated in the self-test display by 1 or 2 question marks. Check the maintenance guide to decode these messages. They do not always indicate a problem. Since this is the first time that the system has been powered up, the language selection menu will appear after the self-test display. This menu allows you to select a keyboard language. Your keyboard language selection will be saved in memory as long as there is power in the battery on the I/O cover. Once this is done, you will see the console prompt on the monitor screen. Next, check the configuration of the system by running the configuration test. If a device is missing from the configuration list or any errors are displayed, review the installation procedures to make sure that every device has been properly connected. If the configuration test still shows discrepancies after the review, or if there are errors indicating a problem, refer to the troubleshooting section of the VAXstation 3520-3540 maintenance guide. This completes the hardware installation and verification procedures. Attach the front panel to the system box and continue with the appropriate software installation procedure. After the system has passed the appropriate tests, set the default boot device. This will direct the hardware to the place where the operating software resides. To set the default boot device, type Set Boot and the device name and hit a carriage return at the console prompt. Once the operating system is installed, the system will use this information to auto-boot the operating software after the self-test has completed successfully. Now you are ready to install the operating software. This can be done a number of ways depending on your system configuration. A diskless system, for example, will have the operating software installed on a host system. The operating software will be downline loaded at boot time. If there is a tape unit in the configuration, the operating system will most likely be built from tape. This concludes the video portion of the Installation Procedures unit. For an example of the steps needed to perform a software installation, see your student guide. In this lesson, we will discuss how to remove and replace some of the VAXstation 3520-3540 FRUs. We will concentrate mainly on options that are probably new to you. The modules in the card cage are protected by metal covers. These covers form a continuous surface that becomes part of the RF shield. The first 3 slots that may contain graphics modules are covered by a single graphics cover. The next 6 slots are covered by the I/O cover module. The Q-bus slots are each covered by a single-width blank cover. When a Q-bus option is installed into one of the slots, the same cover is usually used. However, if the module has I/O, it should have a cover already attached to it. The following removal and replacement procedures assume that power has been removed from the system box and the monitor. The front cover has been removed from the system box and an anti-static kit is in use. To remove an M-bus module from slot 4 through 9, first remove the I/O cover assembly. Optionally, you may wish to remove any cables that are attached to the I/O cover. This is not necessary, but you may find it less cumbersome to work on the system with the cables out of the way. Remove the I/O cover assembly by turning the 4 captive screws 1/4 of a turn, then slowly pull the cover from the card cage. You may now remove and replace any M-bus module. Before you remove a module, you may wish to disconnect the ribbon cable from the I/O module. Removal of the cable is only necessary if you are removing the I/O module. You will probably find that it is more convenient to work on the system with the cover module out of the way. However, removal of this cable also disconnects the battery from the BBU-ROM, and the information that had been previously stored will be lost. Next, we will discuss the procedure to remove a graphics module. Remove the red, green, and blue video cables from the HDI front plane. Remove the cover by releasing the 2 captive screws and pulling it free from the card cage. The graphics front plane is secured to the modules by 3 captive screws. After loosening the screws, gently pull the HDI away from the modules. Be careful to avoid bending any of the connector pins. Remove the graphics subsystem module. After the graphics module has been replaced, replace the HDI front plane. Carefully align the connectors to the modules and apply even pressure to avoid smashing the pins. Tighten the captive screws at an even rate to ensure that the HDI front plane is seated correctly. Finally, attach the cover module and the video cables. The RZ55 and TK70 mass storage devices are both FRUs. The removal and replacement of the mass storage devices that are mounted in the mass storage cage of the VAXstation 3520-3540 system box are similar to the procedures on other systems. On the RZ55, the unit number is selected by jumpers on J2, which is the top connector on the disk drive. The unit number jumper settings are listed in the VAXstation 3520-3540 maintenance guide. The RZ55 device electronics board contains several jumpers. These jumpers are set to the appropriate configuration at the factory and should not be changed. The RRD40 CD-ROM disk drive is the only mass storage device that may be installed outside the system box. The VAXstation 3520-3540 workstation uses the SCSI interface to support a single tabletop RRD40. The data cable connects from the bulkhead on the mass storage cover to the back of the RRD40 drive. This cable is laced underneath the system cabinet. The back of the RRD40 drive has a panel with two I/O connectors. The I/O cable is attached to the top connector on the drive. Because the VAXstation 3520-3540 workstation supports only one RRD40 drive, a terminator must always be installed in the bottom connector. The RRD40 drive is an FRU. The dip switch pack located at the rear of the unit determines the drive unit number. Check the VAXstation 3520-3540 maintenance guide to find the switch settings. In this lesson, we will discuss the procedures used to troubleshoot problems in the VAXstation 3520-3540 workstation. The Power-Up Self-Test, or PST, will be your primary tool in determining failing FRUs and verifying fixes. The first section of the PST, tests F through C, checks initial system integrity and establishes the primary CPU. The countdown is displayed on the LED display on the I/O cover, and the console terminal screen remains blank while this section is being run. Any failures encountered during this initial check will cause the test to hang. If you encounter this symptom, it is usually caused by a faulty CPU. However, it could be caused by something else, such as a faulty I/O or graphics subsystem. Once this initial check is done, the countdown is displayed on the console terminal as well as the LED display on the I/O cover. If an error is encountered from this point on, the individual test that failed will be aborted and the diagnostic will continue on with the next test. After the PST string has completed, any errors will be displayed on the console terminal, and the physical slot number of the failing module or subsystem will be displayed in the LED display on the I/O cover module. Another method to determine problems is by observing the pass-fail LEDs on the modules. Each M-Bus module has at least one LED that indicates the results of the self-test diagnostic. Most modules have a green LED that is illuminated when its self-test diagnostics have passed. On the memory modules, the LED that indicates successful completion is amber. Failure of any pass indicator to light means that the module has failed its self-test diagnostic and should be replaced. As we stated earlier, the PST tests M-Bus modules only. Q-Bus modules are not tested, but the Q-Bus is polled to see what devices reside there. We should point out that even though some Q-Bus modules have a self-test ROM and contain pass-fail LEDs, their tests are not invoked on Power-Up. The pass-fail LEDs on the Q-Bus modules are not a proper confidence check. For example, our system contains a TQK70 controller. The red LED remains on, not because of a failure, but because the module self-test was never run. Once the system accesses the device, the LED will go out. The Power-Up Self-Test console printout lists only one entry for the entire graphics subsystem when it encounters an error. There are two ways to interpret a graphics subsystem error down to the failing FRU. You can use the VAXstation 3520-3540 maintenance guide to decode the error code listed on the console, or you can determine the failing module by interpreting the LED codes on the base module and the graphics front plane. To do this, first observe the green indicator that is mounted on the graphics base module. If it is lit, no error has been detected by the PST. This indicates that the graphic modules and front plane are probably good. If you detect a problem with the subsystem and the green LED is on after the PST has completed, the problem most likely exists in the monitor or cable. While the diagnostic code is being executed, the green LED and one or more red LEDs will be lit. Upon successful completion of the PST, the green LED will remain lit and all red LEDs on the graphics front plane will be off. When the graphic test detects an error, the green indicator will be turned off. To interpret the error, first check LED number 3. This is the rightmost LED. If it is lit, the diagnostic couldn't determine the exact cause of the problem. If LED number 3 is off while the green LED is off, the remaining 3 LEDs will point out the likely bad module. Starting on the left, when LED number 0 is lit, it indicates a faulty base module. When LED number 1 is lit, it indicates a faulty output module. If LED number 2 is lit, it indicates a faulty expansion module. If LED number 3 is off and more than one of the other LEDs is lit, the problem could be in either of the corresponding modules. If the system indicates a graphic subsystem failure and all LEDs are off, the problem is usually caused by a faulty front plane or improper seating of the front plane. Here we have a problem that shows the green LED is off and the red LEDs are off, on, off, and off. The green LED indicates a diagnostic failure because it's off, and the last red LED tells us that the problem is not catastrophic. The failing module is called out by the other three LEDs, with the second LED pointing to the output module as the source of the problem. If you suspect a problem with a monitor or its cabling, you can use an alternate terminal such as a VT330 as the console terminal. To do this, connect the alternate terminal to the printer port of the I/O cover module. With the system in console mode and the terminal powered up, push the halt button in and hold it there. The green LED on the restart run push button will begin to blink. After about 6 seconds, the LED blink rate will increase. When this happens, release the halt push button. Console control will have moved to the alternate terminal, and you should see the console prompt there. You may have to push the return key on the terminal keyboard to see the prompt. Now you are ready to use the terminal to run diagnostics, check system status, or boot the system. To return the console control to the monitor, reset the system. To help diagnose intermittent faults and monitor operating level trends, the VAXstation 3520-3540 is supported by error log analyzers. The Ultrix operating system supports ERF. The VMS operating system supports SPEAR, VAXSIM, and the Analyze Error Log utility. To test QBus options, use the Test MID command. Since the QBus adapter module is always in slot 9 with an MID number of 0, the command will always be T0. This command will test the adapter module and any QBus modules that are present. To test a single module, type T0 and the test number of the module that you want to test. The diagnostics that test the peripheral devices are invoked by T commands. The specific commands that enable you to run the diagnostics for the peripheral devices may be found in the VAXstation 3520-3540 Maintenance Guide. Turn to the Student Guide to see more troubleshooting tips and examples. This concludes the video portion of the troubleshooting unit.